Welcome to Enhancing Mass Spectrometry for Biopharmaceutical Product Development, presented by Genetic Engineering and Biotechnology News. Thanks for joining us today. I'm Tamlin Oliver, Managing Editor of GEN, and I'll be the moderator for this webinar. Today's webinar is brought to you by Thermo Scientific, part of Thermo Fisher Scientific. Our presenter is David Horn, Proteomics Software Strategic Marketing Manager from Thermo Fisher Scientific. He'll be speaking about challenges in the characterization of biopharmaceuticals and the new generation of Orbitrap mass spectrometers. Before we get started, though, I want to encourage you to submit questions for Dr. Horn at any time during the webinar. We'll answer as many as we can at the end of the presentation. Simply type your question in the Ask a Question box on the lower left of your console and hit Submit. Dr. Horn, we're ready when you are.
Thank you, Tamlin. Thanks for inviting me to give this webinar, and thank you to everyone who's dialed in. And what I want to talk about today is describe the application of the latest generation of our Orbitrap mass spectrometers for biopharmaceutical analysis. Next slide, please. So the outline of the talk goes as this. First, I'm going to briefly describe some of the difficulties in the analysis of biopharmaceuticals, followed by an introduction to the next generation of this year's Orbitrap mass spectrometers, followed by much more detail about how the Exactive performs for intact IgG antibodies, followed by an introduction to the protein deconvolution software, a little bit of a detour into software, which is my specialty, followed by some description about the Orbitrap Elite, in this case for top-down analysis of antibody subunits, and then finally I will summarize. Next slide, please. So let's start describing some of the challenges in the characterization of biopharmaceutical drugs. Next slide, please. So this slide is kind of an interesting overview of the challenges of antibody characterization. And one of the nice ways to view this is to look at a small molecule drug, in this case aspirin, which is 180 Daltons, relative to the large molecule drug, the monoclonal antibody, which is about 150,000 Daltons. And you can see, based on the scale, the monoclonal antibody is considerably larger. So aspirin has about 21 atoms in the chemical formula. There's not a whole lot of different ways that things can go wrong with aspirin, and they're fairly easy to characterize because it's such a small molecule. For the monoclonal antibody, it has 20,000 atoms, has tertiary structure, secondary structure, quaternary structure, a lot of different ways that things can go wrong. So this requires very powerful analytical tools for a scientist to be able to characterize this molecule accurately and confidently. Next slide, please. I think many of you on the call already know this, but this is the schematic of a structure of an antibody. So an antibody has two light chains, each about 20 kilodaltons, and it has two heavy chains, each about 50 kilodaltons. They are held together by internal and interchain disulfide bonds, and there's a conserved glycosylation site on the CH2 domain, on the FC domain on the antibody. The glycans are heterogeneous, so there is not one mass for the structure of an antibody, but actually there are several masses, and I'll show examples of this later in the presentation. Now, since this is a protein, like any protein, there are various ways that it can degrade. Deamidation is a very common occurrence on proteins, which is the conversion of an asparagine to an aspartic acid, a 1 Dalton shift. Oxidation readily occurs at methionines and other locations. Disulfides over time can break and then reform with the wrong disulfides in the structure, which causes misfolding and can lead to things like aggregation. The sequence can be truncated, so you don't express the full form of the protein, but you can actually at some point express only a partial sequence. And the glycosylations can fall off. You can also have the wrong population of glycosylation. So there's a lot of different ways that things can go wrong. Now, one of the interesting things about almost all these degradation pathways is they induce a change in the mass. So if you have a mass spectrometer that can measure masses accurately, you could actually, in a lot of cases, detect those changes on either the intact antibody or at least on the light chain or the heavy chain. Next slide, please. This is a bit of a complicated slide. I'm not going to go through it in a huge amount of detail, but what I do want to point out is that, and I think many of you know, that due to automation upstream and downstream, from the analytical characterization of these antibodies, there's an increasing number of antibodies that need to be analyzed. And so anything you can do to increase the speed of your analysis and your throughput lab productivity is extremely welcome nowadays. I'm only going to focus on the types of analyses that will happen kind of upstream in the development of antibody-based drugs, and I want to talk about what we see over here as product ID, so intact mass measurement, and to some degree, how much of the sequence can you confirm with that intact mass measurement and other types of analyses, and to some degree, because there's some glycan heterogeneity that you can detect on the intact mass, we'll be mentioning some glycans in a little bit of detail. Next slide, please. So one more thing I want to point out is that recently Dionex came into the Thermo Fisher fold, and so that has given us many more tools for antibody characterization than we had at Thermo Fisher prior to that. So they have a very nice multi-dimensional separation for protein charge variant characterization, a number of columns that are very powerful for protein separation, ion chromatography systems, they're a world leader in that, and they came in with their Chromeleon data system, which we can combine with Excalibur, so for some very powerful analyses. And then finally, before we get into today's focus, we also sell quite a few reagents for protein science, and so we have a lot to choose from. But today's focus will be on the mass spectrometers. Next slide, please. So now, after that brief introduction, I want to get into the new generation of Orbitrap mass spectrometers, the Q Exactive and the Orbitrap Elite. Next slide, please. So this tree is showing that we have a new season in the life of Orbitrap mass spectrometry. We have new branches that are growing out of the tree, and the ones that are circled are the Q Exactive, the Orbitrap Elite, and the Orbitrap Velos Pro, all of which have been released this year, launched at ASMS. And I'm not going to talk about the Orbitrap Velos Pro. It's very similar in features to the previous LTQ Velos Orbitrap, although the ion trap has been improved. What I do want to talk about are the Orbitrap Elite and the Q Exactive for antibody characterization. Next slide, please. So for those of you who don't know what an Orbitrap is, this is what it looks like. So it's a type of ion trap. So ions are injected into the Orbitrap, and they fly around the trap. They kind of bounce back and forth on the z-axis that we can see here at a frequency that's proportional to its mass over charge. So if we can detect the frequency using image current on the plates on the side of the Orbitrap, we can perform a mathematical calculation called a Fourier transform that translates this, what's called a transient, into a mass spectrum. And the reason why these Fourier transform-based mass spectrometers are so powerful is that if you detect that ion frequency for a long period of time, you get better and better confidence in the frequency that you measure, which means you have better mass resolution and better mass accuracy. Next slide, please. So the Q Exactive and the Orbitrap Elite, I mentioned a few slides back. What's new relative to the previous generation? So I'm not going to talk about all the things that the Orbitrap systems do. I'm going to talk about what's changed in the Orbitrap systems that make these especially powerful for intact protein analysis. So first of all, the Q Exactive is the next generation of our Exactive product line, and there are a lot of changes since the Exactive was released. So first of all, the Q in the Q Exactive stands for a quadrupole mass selector. So now you can isolate narrow ranges or even very wide ranges of M over Z for further analysis downstream. Secondly, there is an HCD cell, which performs collisional activated dissociation. Some of you may be familiar with this on the LTQ Velos Orbitrap and the Orbitrap Excel systems. This one has a very sensitive and high throughput implementation of this HCD cell. And has the same Orbitrap as before, but there's new advanced signal processing and electronics. So the way that we detect the ions during the acquisition, we actually end up with 2 times the resolution than we did on previous generation of Orbitraps, and I'll show examples of that further in the presentation. Also has improved ion optics over the original Exactive, so it's more sensitive. And what the Q Exactive gives you for intact protein analysis is high sensitivity, very high throughput, and what you'll see is very, very nice looking, clean looking intact protein spectra. Now, the Orbitrap Elite is our next generation of our Orbitrap product line. That would be the next step past the LTQ Velos Orbitrap. And the big addition to this instrument is the new compact high-field Orbitrap. So this is a new Orbitrap that's unique to the Orbitrap Elite that produces even higher resolution than all the previous generations. Also, we've swapped the ion trap with the Velos Pro, which has some nice new features. And like the Q Exactive, we have advanced signal processing and new electronics. You not only have the resolution enhancement from the high-field Orbitrap, but you also have it from the signal processing. And finally, improved vacuum, which makes detection of intact proteins in the Orbitrap more sensitive. And what this instrument really provides is ultra-high resolution and ultra-high mass accuracy. Next slide, please. So here's an example of what that advanced signal processing does. It's not just actually an algorithm that does this, but it's brand new electronics that were necessary to be able to do this. And what it does is for the same transient detection time, so the transient is how we do the frequency detection in the Orbitrap, the resolution is doubled. So this is the same sample on an LTQ Orbitrap Velos versus an Orbitrap Elite. It's a single charge state of a 47 kilodalton protein, yeast enolase. It's a pretty big one. And on the Orbitrap Elite, with these new electronics, we're able to resolve the isotopes down to the baseline. That's a really actually impressive spectrum, especially compared to the Orbitrap Velos. The Orbitrap Velos by itself already had very, very good resolution. So with this higher resolution, we have a nicer distribution of isotopes for that enolase ion, and then we could more easily deconvolve the spectrum, and also we'll get better mass accuracy. Next slide, please. So this advanced signal processing doesn't just help for isotopically resolved samples, but we've also observed that it's very helpful for intact proteins. So this is a spectrum of IgG, about 150 kilodaltons, same sample detected on both the Orbitrap Elite and the Q Exactive. And what we noticed was that in the mass spectrum itself, the signal is so clean, it almost looks like a deconvolved spectrum itself. Glycoforms are very clearly resolved. Each of those glycoforms are spaced by 162 daltons, which is a hexose. And the spectra are of relatively equal quality between the Orbitrap Elite and the Q Exactive. Even though the resolution setting is 15,000 or 12,500, we actually have very high resolution of these unresolved intact proteins. Next slide, please. So that's a basic overview of the two new mass spectrometers. Now let's go into more detail about the Q Exactive and how it performs for intact protein analysis. Next slide, please. So here's a zoom in of the schematic of the Q Exactive MS. So I've already described many of the features, but we can focus on, first of all, the quadrupole mass filter. So we can transfer a very wide range of M over Zs, 50 to 4,000. We can do precursor selection, SIM scans. We can do MSMS in the HCD cell. So that allows you to do some top-down type of analysis on intact proteins, but I won't discuss that here. I will discuss that for the Orbitrap Elite later in the presentation. And the Orbitrap Mass Analyzer, which has resolution 140,000 and M over Z 200, very high mass accuracy, and that advanced signal processing. Next slide, please. So here's another example. I already showed you one example of an antibody on the Q Exactive, but this is an antibody where we actually know the sequence. So we ran this in the instrument, and what we noticed was that, first of all, the signal noise for this sample was extremely high. There was very little baseline or background, and so these peaks were extremely clean. Also, there's a very smooth distribution of charge states across from 1,800 almost to 4,000 M over Z. And again, like I had mentioned before, that if you look at any one of the individual charge states themselves, it almost looks like a deconvoluted spectrum. The peaks are so well shaped and they're so clean. Now, this was not a lucky shot at it. We actually have looked at many, many data files now of antibodies of various masses and size on the Q Exactive, and almost all the spectra that I've seen for these antibodies look just like this. Next slide, please. And this is a deconvolved spectrum of that same input spectrum from the previous slide. And as we normally have to do for electrospray mass spectra of large intact antibodies, we needed to do an algorithm called deconvolution. For those of you who are not familiar with that deconvolution algorithm, it takes a mass spectrum, like the one we had in the previous slide, and converts it to a zero-charge mass spectrum, or just a mass. And what happens is all the charge state for a given component from the previous spectrum are collapsed into a single peak at the mass, the average mass value of that protein in the spectrum. Now, in this case, we can take the masses that were produced from the deconvolution and match it to the theoretical average mass for our antibody peak and include the various glycoforms that we would expect to have on this antibody. And in red on the spectrum are the mass measurement errors that we have for each one of those peaks. And we're actually pretty surprised to see that all of the peaks were within 12 ppm, which is less than 2 Dalton, plus or minus 2 Dalton mass accuracy. And that mass accuracy even was just as good for the peaks at very low abundance. So if we look at the peaks at 146,600, the G0F, G1F, there was some deglycosylation going on, it looks like. And those peaks are at a 2% level, and they're still sub 10 ppm. We can also look at the G2F plus G2F. That's also at a very low level, and that's 12 ppm. So we have very consistent mass measurement accuracy even for low abundant peaks. That was a surprise, actually. But we've actually seen this repeatedly from spectrum to spectrum, which I'll show in a moment. But also, we are also impressed by this respect deconvolution, that the output spectrum is extremely clean. You only see the peaks of interest in the data, and you don't see background noise. And I'll get into a little more detail about the respect algorithm a little bit later in the presentation. Next slide, please. So one thing our new protein deconvolution software allows us to do is to go back and look at all the peaks for all the charge states for a specific deconvoluted mass. So in this case, the largest, most abundant mass, this one for the G0F, G1F, has a mass of about 148,217. And if we go back to each of the charge states, what we can do is take the measured M over Zs for each of those charge states and multiply them out, just calculate it out to see what the calculated mass would be if we only took that specific peak into account. And what we were also surprised to see was that the mass deviation for each of those charge states hardly deviated from the mass we had from the deconvoluted spectrum itself. That means that you can take any one of those individual peaks from this spectrum and use that as the deconvoluted mass, and there's basically no difference from the deconvoluted spectrum. And that's a testament to how nicely shaped those peaks are in the raw data and how well resolved they are. Next slide, please. So we actually went ahead and did that. So instead of deconvolving, we took the M over Z values for one of the charge states, in this case the 52 plus of IgG. So here are the top 5 glycoforms, G0, G0F, and so forth. We took the M over Z values from the raw data, and we compared that to what the theoretical masses are supposed to be for each of those different glycoforms. So notice this spectrum looks like a deconvoluted spectrum, but you can see at the bottom we actually have an M over Z axis. So our mass accuracy in the raw data is quite outstanding, actually, for our intact proteins. Next slide, please. So as I mentioned before, we wanted to make sure that this was not something that we could just pick one lucky spectrum and get good mass accuracy for. We wanted to see not only if we could see that in other data files, but we also wanted to see if it was reproducible in abundance across several data files. So we took that same IgG sample, we ran it 7 different times with various different LC gradients. So we didn't have the same gradient, we actually changed it up. And we ran it on 2 different Q Exactive systems, so it's not all in the same system. And they were acquired on 3 different days. We deconvoluted all our mass spectra using the protein deconvolution software, which I will talk about in the next section. And we measured the mass and the relative abundance of each of those 5 major glycoforms across all 7 of those different samples. Next slide, please. So what we see here is a table of the results for those 5 different glycoforms, the ppm mass errors across the 7 different runs. So if you look at the first column, that's the raw file number. Those are the 7 different raw files. Second column is the instrument that we use, the Q Exactive number 1 or Q Exactive number 2. And then the rest of the columns are the IgG glycoform and the ppm error off of the theoretical mass for each of those IgG glycoforms for those different runs. So what we found was that the mass errors were actually rather reproducible. Most of them were within 12 ppm or 13 ppm or so. And one interesting thing that we found was there was actually an average offset of minus 7 ppm. And I'll talk about that in a moment. But the spread, the standard deviation of the spread of mass accuracy errors is 6.4 ppm. So we think that's a better indication of the mass tolerance of the system. The minus 7 ppm corresponds to roughly 1 Dalton. This is kind of interesting because it's actually rather difficult to calculate a theoretical average mass. So depends on the carbon source where you grow the protein of actually what the average mass will be. So any minor change in the carbon-12, carbon-13 ratio can change the mass of the protein upwards of 1 Dalton at least, if not more than that. So that minus 7 ppm may just be due to the fact that we're using average masses for a protein that has a slightly different source of carbon than what we use to produce the theoretical masses. So then again, we think that that 6.4 ppm spread is a more realistic indicator of the mass accuracy. And further, we've run plenty of peptide and small molecule samples on these machines, and we do not see that 7 ppm offset. Next slide, please. So the next table is we took those same raw files. So we see the raw file on the left side and the Q-exactive number on the next row. And now we are calculating the relative abundance of each of those glycoforms to the most abundant G0F, G1F. And so what we see is, say, for the G0F plus G0 column on the left side, is that the CVs for the abundance measurements are 3.4%. We get very reproducible abundances. One thing of interest, though, raw file number 2 was actually a markedly different gradient than all the other ones, and it turns out that there were some other species that were co-eluting that interfered with the abundance of the higher mass glycoforms. So 6 out of the 7 of those runs have very reproducible measurements, and then one of those runs looks like an outlier. And that tells us about the sensitivity of the method, that raw file number 2 with a higher G0F, G2F, and higher G1F, G2F, there's something wrong with that sample. There's something different about that sample. So it looks like our sensitivity based on these data are actually within a few percent. Next slide, please. So then we got to thinking, what does this low mass error mean? So if we have 10 ppm mass error, say, for example, or we have 15 ppm, is there something on an intact antibody that we can detect? So not really much that you could detect on an antibody that large. If you have several deamidations, you might be able to detect it. But one thing you could detect is whether or not some of your disulfide bonds have been reduced. So at 10 ppm accuracy, you could detect, say, 2 or more disulfide bond reduction. Or 15 ppm, you could do 3. And it turns out actually on the Orbitrap Elite, and I'm not showing this data, but this has actually happened. So we had the sample sitting in something it shouldn't be, and it shifted the mass of the protein by 6 Daltons. So at 6 Daltons, that's 3 disulfide bonds, and so you would need confident about 15 ppm mass error to be able to detect, actually 20 ppm to be able to detect those 3 disulfides shifting. And based on the data that we just showed, we can confidently detect a shift of that large. Next slide, please. So in summary, we think that the Q-exactive produces extremely high mass accuracy for intact antibodies. Not only high mass accuracy, but really clean, high-resolution spectra. These masses and abundance can be very reproducibly be measured for the sample from run to run, and this indicates that the Q-exactive will be an excellent instrument for high-throughput confirmation of intact biopharmaceuticals. Next slide, please. So now let's take a little diversion into software, which is my specialty. And I had shown you in the previous section of a deconvoluted spectrum that was produced by Respect, but also those reproducible masses and relative abundance levels were also produced by Respect. So in the creation of these instruments, we also needed to create a brand new protein deconvolution algorithm that can match the quality of the data that's produced by these Orbitrap-based systems. And I'll give you a brief demonstration of what this software looks like. Next slide, please. So the software is going to be called, sort of obviously, Protein Deconvolution 1.0. It's a workflow-based software for intact protein mass determination that supports all of our Orbitrap mass spectrometers. There will be a future version of the software that also supports ion trap mass spectrometers, but we will not have the same mass accuracy on the ion traps that we do on the Orbitraps. It includes 2 deconvolution algorithms. So we, on our Orbitraps, have to deal with the fact that we can have some very large proteins with isotopic resolution, and that requires a different algorithm for deconvolution than the one that we use for RESPECT, the RESPECT algorithm, which can handle unresolved proteins. So fortunately, we've had an algorithm in-house for several years called Extract that has been in wide use in ProCyte PC, our top-down proteomic software, as well as it's actually in Qual Browser for protein and peptide determination, and some people are actually using it in Proteome Discoverer. So we're rather confident in this algorithm's ability to produce monoisotopic masses, and we licensed the RESPECT algorithm from a company called Positive Probability Limited. After evaluation, we found that it produces extremely accurate results for unresolved isotope distributions. So as of the recording of this webinar, it's not out yet, but it'll be out very soon. And if you want to learn more information, you can monitor our thermoproteomic software portal. I want to mention that this software portal has a lot of information about our current software products for proteomics, so Proteome Discoverer, Protein Center, Sieve, Pinpoint, ProCyte PC, and we will be adding content for the protein deconvolution on there as well. It's not there right now, but keep checking and it'll show up soon. Next slide, please. So here's a screenshot of what you see when you first load the protein deconvolution software. So you have a couple options of experiment type or for algorithm type. First is an extract algorithm, which does the isotopically resolved deconvolution, and RESPECT deconvolution, which is the isotopically unresolved deconvolution. So it depends on your sample. If you have an Orbitrap Elite and you're looking at the light chain and heavy chain of an antibody, you're probably going to choose extract. If you're doing intact IgGs, you'd probably choose RESPECT. Then after you select your algorithm, you select the data file you want to analyze, and then you can either select an existing method, and those methods contains parameters for deconvolution and also for chromatographic selection, or you can create a new one. So if you say create a new method, you go to the next screen. Next slide, please. So what we see here is the list of parameters. There's basic parameters up top, which are ones that users will change more often, and advanced parameters down below that pretty much you'd need to be an expert to really want to change. A couple of parameters you're probably used to by this point for those of you who have done deconvolution. So you have an input M over Z range and an output mass range and a mass tolerance, charge carrier, and so forth. One of the interesting tools we've given users is that RESPECT requires a peak model, and I think most, if not all, deconvolution algorithms require that. Instead of requiring the user to figure out what that is, we understand how peaks are shaped on our Orbitrap systems. So instead of a peak model, we ask the users to give an estimate of the target mass. It definitely does not have to be accurate within ppm level. It can be 10 or 20 kilodaltons off. But what that target mass does is it tells the software to calculate a peak model based on a protein of that mass at the resolution of the instrument that's shown down below. We are not asking the users to supply that resolution. That resolution is autofilled based on the raw data file. So the more accurate that peak model is, the more accurate results are going to be, and the more sensitive that result is going to be. Next slide, please. So the next tab is a chromatogram tab. So you have some options on the type of chromatogram you want to display in the middle panel. You can choose a total ion chromatogram or a base peak chromatogram. In the next release of the software, there's going to be a UV chromatogram. And then you can take that chromatogram and you can average across a number of different scans to produce an average spectrum down below. Normally you would average across the peak of the chromatogram for that given protein. For those of you who are Qual Browser users, this works very similar to the way the Qual Browser does the averaging off of a chromatogram. Next slide, please. Then the next step, of course, is to do the deconvolution itself. So you can see in red at the top it says fast data processing 1 to 2 seconds. That was one of the parameters that really attracted us to RESPECT, is that in maximum entropy type algorithms, at least in my experience, if you do a wide mass range, it can take several minutes for that algorithm to complete. RESPECT is almost instantaneous, 1 to 2 seconds, and it doesn't really matter how wide your output mass range is. It only matters generally how complex your input spectrum is, but again, only a couple seconds max to produce that deconvoluted spectrum. So at the top, we have the spectrum that we just created in the Chromatogram tab. In the middle panel is the deconvoluted spectrum. In this case, it's respect deconvolution. If you do extract, it'll be extract deconvolution. And then down below are the results of the deconvolution in the table form. So if you click on any of the rows in the table, you will highlight the peak in the deconvoluted spectrum, and you'll also highlight all the peaks in the original spectrum that was used for production of that deconvoluted spectrum. So one thing you can do is there's a little plus sign on the far left of the table. You may not be able to see that with your screen resolution, but once you click on that plus, another level of the hierarchy of the table will show up with the list of all the charge states that have been detected for each of those deconvoluted components. And like I had shown for the Q-Exactive section, it'll also show the calculated mass for each of those charge states, and you can get an idea of how reproducible that mass is measured across the whole set of charge states. One more thing you can do is you can right-click on that table and export to Excel. So if you want to do anything else with that, you can. And finally, on the far right side of the table, you'll see that there's a delta mass. So right now it takes the most abundant peak as the reference peak, and then calculates the mass of all the other peaks relative to that reference peak. So you can see that the second item in the table is 162 Daltons from the first, which is a hexose. The third row in the table is 324 roughly Daltons, which is 2 hexos. Next slide, please. So finally, you'll be able to create a report. And what this report is automatically generated. It has all sorts of information. It has the sample information it pulls from the raw file. It has the chromatogram parameters that you used to generate the chromatogram in the 2 tabs previously. It'll show the source spectrum. It'll show the deconvoluted spectrum. It'll show a deconvoluted peak table, and also evidence for each of those peaks, deconvoluted peaks, in the raw data. So this report can be printed. It can be saved as a PDF. So in summary, this protein deconvolution software provides very confident deconvolution results, either by extract or respect. It's going to be out in November. It'll be on our price list. And one thing I want to point out is that we're being very aggressive about the releases of this software, so we're not going to wait a year for protein deconvolution 2.0, but we're trying to release it in 4 to 6 months. And like with all of our proteomic software, we keep upgrades as inexpensive as possible. So going from 1.0 to 2.0 won't break the bank. Next slide, please. Now that we have been diverted by software, let's get back into hardware. So we'll talk about analysis of antibody subunits using the Orbitrap Elite hybrid mass spectrometer. Next slide, please. So here's a schematic now of the Orbitrap Elite, and this system has all sorts of tools for doing protein characterization. So first of all, it has an ion trap in the ion source. And what that ion trap allows you to do is CID, so you can take a charge state of a protein, and you can do a resonance excitation to cause a specific type of fragmentation, which is actually in general a little bit different than what HCD does. So actually doing CID and HCD in the HCD cell can give you complementary information. Also, the ion trap allows you to do MSN. I'm not sure you'll be doing too much MSN in the ion trap on intact proteins, but if you do have glycans laying around that you want to identify, MSN is absolutely critical for doing that. Also, we have a third type of MSMS, electron transfer dissociation, and that's actually a critical component of doing biopharma analysis, largely because the IgG heavy chain has those conserved glycosylation sites. If you do collisional activation techniques, those glycosylations will fall apart first, and you basically don't get any backbone fragmentation. With electron transfer dissociation, you cleave only the amino acid backbone. You don't cleave the glycans, and so what you end up getting is a large amount of sequence coverage by ETD you wouldn't be able to do any other way. So that's very important. So you have 3 types of MSMS modes for sequencing, and this instrument is about as good as you can find for protein sequencing, whether it's bottom-up or top-down. Also, second but not least is the new compact high-field Orbitrap analyzer, and I already mentioned this. It has 240,000 max resolution, very low ppm mass accuracy, and this new Orbitrap is unique for the Orbitrap Elite. Now, just kind of as an aside, my background's in top-down proteomics, so I came out of Fred McClafferty's lab doing FTICR, And all this time, it was always nice to see 200,000 resolution on the FTE, and I kind of missed it. I don't miss it anymore. This instrument has replaced the FTE, in my opinion, for this type of analysis. Next slide, please. There's a little bit more detail about this new compact high-field analyzer. So they actually took the original Orbitrap and made it smaller. So by making the Orbitrap smaller, keeping voltages about the same, the electric field inside the Orbitrap is higher. With higher electric field, you get higher frequencies of the ions bouncing back and forth. And so with higher frequency, if you detect over the same amount of time the way the Fourier transform works, you get 2x improvement in resolution. So this reduced Orbitrap size results in a 2x improvement. And then you combine that with the advanced signal processing that we provide also with the Q Exactive, that makes it another factor of 2 higher. So this is actually for the same transient duration, 4 times higher in resolution over the previous generations of Orbitraps, which means we can easily get up to 240,000 maximum resolution. And in the process now, we can fairly easily resolve proteins as large as BSA. And I just saw this last week, whereas this beautiful spectrum, 67 kilodalton protein, baseline isotopically resolved. Next slide, please. So I want to kind of point out for those of you who are unclear on the difference between isotopic resolution and the advantages of having isotopic resolution versus being unresolved. So this is kind of an artificial experiment where we ran the same sample at 15,000 resolution, which means we detected the transient for shorter, as well as 240,000 resolution, which means we detected it for longer. And so as you can see, the longer we detect, the more confident we are in the frequencies of those various isotopes, and then we can start to resolve them easily. This is the IgG light chain is about 24 kilodaltons. So by having these narrower peaks, you can just do it by having narrower peaks, you're actually going to have better mass accuracy. But also by having isotopic resolution, you have much higher peak capacity. So if you're doing top-down analysis, you really need high resolution because there'll be so many isotopic clusters in the spectrum, they'll start to overlap each other. Another added advantage of having isotopic resolution is that each of those isotopes are separated by 1 Dalton in mass, but because you detect the spectra in the M/Z units, you can actually tell what the charge state is of that isotope cluster by just measuring the M/Z difference between any 2 of those peaks and then doing 1 divided by that, and that tells you what the charge state is. You can actually figure out what the charge state is of an intact protein based on 1 isotope cluster alone, whereas if you have unresolved isotope distributions, you will need to run a deconvolution algorithm. Next slide, please. So here's an example of an isotopically resolved IgG heavy chain. In this case, we were not given the target mass, so I don't know what that target mass is supposed to be. But I just wanted to point out that we can do this very easily on an LC timescale. This is a 54 plus of an IgG heavy chain with a mass about 50 kilodaltons. Acquired a 240,000 resolution on the Orbitrap Elite, and it was baseline resolved. And if you take any 2 of those peaks and look at the distance between them, the delta M/Z is 0.018. That's extremely high resolution. Next slide, please. So what does low ppm mass measurement mean? So with isotopic resolution, we can pretty much guarantee sub 5 ppm mass accuracy. So what is sub 5 ppm mass accuracy on a heavy chain, 50 kilodaltons or so? About 0.25 daltons. That means almost anything that happens to that protein that changes the mass will be detectable. So if you have a significant amount of deamidation, that will show up. Any 1 disulfide reduction will clearly show up in the mass of that protein. And so pretty much almost any amino acid substitution except for maybe glutamine to lysine will also show up. So if you detect with isotopic resolution that heavy chain and it matches the target mass of what it's supposed to be, that means you're very confident that what you have is correct, at least in terms of chemical formula. Next slide, please. So now we're showing an example of the IgG light chain. Now we're back to the same IgG that we were using with the Q Exactive data. And one thing we noticed, so we reduced the IgG light chain from the heavy chain, from the intact antibody, and then we ran LCMS on it. And what we found for this specific light chain is during the reduction, our target mass, if everything was reduced, all the disulfide should have been 23,428, but we actually measured 23,424. So that's a 4 Dalton difference. And again, that 23,424 Dalton measurements was produced by Exactive, as you can see on the bottom left quadrants. So that clearly makes you think that it's 2 disulfide bonds, but we don't want just to assume that's happening. We want to confirm that it's happening. How do we do that? Next slide, please. So there's a couple ways to go about doing protein confirmation, the localization of modifications. Generally what people will do is to do what's called a bottom-up protein analysis. So what you do is you take an intact protein, you digest it, say, with trypsin or lyc or some other enzyme, and you do a peptide mass fingerprint or even data-dependent MS-MS. So peptide mass fingerprinting can have some disadvantages because there's no guarantee of 100% sequence coverage. You might have very hydrophobic peptides. You might have short peptides, 2,3 amino acid. Could potentially make peptide mass fingerprinting rather difficult. And also, it's just an additional step that you have to run. So there is an alternative to bottom-up proteolysis called top-down proteomics or top-down protein characterization. Again, this came out in the Coffee Lab, so I've been heavily indoctrinated into this philosophy. But the basic purpose of the point is that you take your intact protein and then you just fragment it on the intact. You don't digest it. So you can do this type of sequencing without requiring another experiment. So for those of you who would be new to top-down, I have a couple references below. The first one is the original paper by Neil Kelleher in the McCrafty Lab that talks about top-down versus bottom-up protein characterization and why top-down is advantageous. And the reference below that, this data that I'm going to show you is not the first time we've done top-down on our instrumentation on an antibody. And there's a publication from a few years back by Pavel Bondarenko at Amgen where they did top-down HPLC MS-MS of light chain and heavy chain of an antibody on an Orbitrap system. Next slide, please. So we took that intact protein and we did electron transfer dissociation on it. So you can see what the MS-MS spectrum looks like down below. It's a very high complexity. Also, the fragments have very high signal to noise. And if we just take any region of the spectrum and zoom it up, you can see that there's lots and lots of information. So in this case, it's about 12 homers wide. There's at least 10 isotopic clusters in there, if not more. And there's locations where those isotopic clusters overlap each other in M/Z space, which means you need extra high resolution to make sure you can identify those isotopic clusters. So again, we can use the extract algorithm. It doesn't matter if we have simple or complex data. We can use extract to deconvolve the spectra and produce mass values, in this case over 200 mass values for the light chain. And then we search the results in a piece of software called ProCyte PC. I don't have a lot of time to talk about ProCyte PC. This presentation is something that we've had for multiple years now. But ProCyte PC is a software package for top-down protein identification, and it can certainly be used for looking at antibodies. So in this case, we put the IgG light chain sequence into ProCyte PC, and then we did one extra kind of interesting thing where ProCyte PC has a mode called, quote-unquote, disulfide mode. And disulfide mode then assigns a 1 Dalton negative mass defect for each of the cysteines on the sequence. So if we have a disulfide bond between two cysteines, fragments that contain that disulfide bond will be 2 Daltons smaller than would be otherwise. So in this case, you see a fragment map in the inset, and so all those fragments are in the middle of the sequence, and every one of those contains a quote-unquote disulfide modification. So that localizes the disulfides to those pairs of cysteines, and actually those are the disulfides we would expect for the light chain. So in one experiment, not only do we confirm that those disulfides are there and their localization, but we also have complementary fragments, N-terminal and C-terminal fragments in the middle of the sequence, which matches exactly what that sequence should be from that point to either termini, which means we have 100% sequence coverage. Next slide, please. So we did the same thing with HCD to see if we can get more information. And in this case, it was an even more complex spectrum, which was actually kind of surprising. ETD is usually extremely complex in itself. But after extract, we produced greater than 500 mass values. Again, used ProCyte PC. And in this case, the E-value was 10 to minus 26. One thing I forgot to mention in the previous slide, that E-value was 10 to minus 16. These are E-values that you would not commonly see in bottom-up proteomics. ProCyte PC produces very confident matches. So in this case, we see a large number of fragments in the middle of the sequence, but we also see fragments close to the termini. and nearly full sequence coverage on the C-terminus. And again, the fragments in the middle include this -2 Dalton disulfide modification, and so we further confirmed by an alternative MSMS technique that this is the structure of this protein. Next slide, please. So here's a zoom in of the top-down fragment map. So the known disulfides for the light chain are shown over the sequence, and the fragments actually match that. Turns out across both the ETD and the HCD, there are 21 pairs of complementary fragments, and these confirm 100% sequence coverage. So we got 100% sequence coverage on the sequence without running another experiment. If you are running your intact protein, you do automatically trigger of MSMS, you will get this type of sequence information at the same time you're measuring the intact mass, and that's one experiment. Now, combining the ETD and HCD results produces more fragment backbone cleavages than you would by either one alone. I assume that with CID, you'll increase that further. And then no fragments are identified between the disulfide-bound cysteines due to that cyclization. So you could get a fragment backbone cleavage in there, but because the disulfide bond is attached, that you will not separate the protein. It will stay intact. Next slide, please. So in summary, I only showed one actually intact protein spectra off the Orbitrap Elite, Unresolved, and the antibody, but Orbitrap Elite is well suited for that type of characterization, as well as top-down protein characterization, of course, as well as bottom-up protein characterization. It's a terrific instrument for proteomics type of analysis. Next slide, please. So in conclusion, I hope I have shown you that Orbitrap-based systems are excellent for biopharmaceutical characterization, and the Q Exactive and the Orbitrap Elite are the best systems that we've produced yet for intact biopharmaceutical analysis. Software protein deconvolution produces highly accurate and confident intact protein masses and abundance, and ProCyte PC is definitely applicable for biopharmaceutical applications. It's not just the software for top-down proteomics. It says that the biopharmaceuticals are proteins too, so ProCyte PC works just fine. And finally, these high-confidence results can allow you in your biopharmaceutical lab to increase your sample throughput by essentially bypassing more time-consuming experiments, say peptide mass fingerprinting, or if you have very high mass accuracy on the intact protein, you might find a modification that you wouldn't have otherwise. Next slide, please. So just one thing I want to point out is, so I've been talking again about mass spectrometry and software, and Thermo Scientific produces a lot more products for biopharma than just these mass spectrometers, as I mentioned a little bit before in the dynamic slide, so please check it out. And Thermo is more than a mass spec company. Next slide, please. So there's a lot of people to acknowledge. My colleagues in proteomics marketing, the demo chemists have been very helpful. Software R&D who produced the protein deconvolution algorithm. And if I put everybody in hardware R&D who actually worked on these instruments, it would go way off the page. But primarily thank Alexander Makarov, who's the inventor of the Orbitrap, and Jay Schwartz, who runs our ion trap side of things. Martin Zeller, who produced a lot of the intact protein data that we showed in recent conferences and in this presentation. Next slide, please. And I want to thank you for attending this webinar, and back to you, Tamlin.
Thanks, David. All right, let's start our Q&A discussion. We have a lot of good questions already, but do keep them coming, and we'll answer as many as we can. All right, David, you ready for some questions?
I'm ready.
Our first one is, can I perform these experiments with the earlier versions of OT instruments?
Yeah, so we can perform intact protein analysis on previous versions of the Orbitrap instruments, and we have quite a few application notes and presentations that show that. I can refer back to the top-down paper from Pablo Bondarenko and colleagues at Amgen, and a number of others. Actually, one other related question is, can I use the protein deconvolution software with my earlier versions of Orbitraps? And the answer is yes. The protein deconvolution software works with any Orbitrap-based system at this point.
Okay. Our next question is, how do these compare to TOF?
Yeah, that's a kind of a tough question to answer, mainly because I don't have a direct comparison for the most part of exactly the same sample, but in my experience, I've seen a lot of data files from top systems, and I just noticed that the Orbitrap systems, especially the latest version, produce very clean-looking data, and as I'd mentioned before, that the spectra for the intact protein, the raw data almost looks like a deconvoluted spectrum by itself, and as I'd mentioned before, I have seen this time and time again on the new generation of instruments. So at this point, in general, the spectra do seem to look cleaner.
Okay. How do you know the mass difference was due to glycosylation, not something else?
So I believe this question came from back at the first set of intact antibody spectra, and for the most part, we know the sequence and we know the forms for the antibodies that we're looking at. They're already well characterized. So we already know that the mass difference between those peaks are due to glycosylation. Also, the mass accuracy of these instruments is so good, as I also showed in a bunch of slides, that when we have that kind of low ppm level and we're observing very close to 162 Dalton difference between the glycoforms, that gives us a very good indication that that's really what's going on.
Okay. What column do you use, or did you use, for the intact protein analysis on the 7 gradients?
Very good question. I apologize for leaving that out. I have to confess I'm not a chromatographer, but given that the column that we use for all of those studies is called a ProSwift column, and that's a product of Dionix, now Thermo Fisher.
Okay. And here's a question I don't understand. What are the beats, or what are beats?
Yeah, so I guess I dropped that in the middle of the slide. These things kind of fly out of my mouth as an FTMS person. I didn't show a picture of what a transient looks like, the actual signal that gets detected in the Orbitrap. What happens is when you have isotopic resolution, all the various isotopes for a given component go in and out of what's called in and out of phase. So they kind of spin around at different frequencies. When they come back into phase, which happens periodically, you get this spike in the signal that we call a beat. And the more of these beats that you detect, the better the resolution that you ultimately get in the final mass spectrum. Apologize for dropping that terminology.
Okay. Can you analyze greater than 50 kilodaltons with isotopic resolution?
Yeah, so we did show a spectrum of the heavy chain at 50 kilodaltons that did show isotopic resolution. What I didn't show is we've also actually gone through the same process as in the Orbitrap Elite for intact bovine serum albumin as well as enolase. So we can get isotopic resolution on BSA on this Orbitrap Elite without a huge amount of effort. We can also do top-down on proteins up to that size and get a reasonable amount of sequence coverage, again, without a huge amount of effort.
Okay. Does the smaller size of the Orbitrap cell and Orbitrap Elite affect its ion capacity? That is, will it hold less ions than normal Orbitrap cells?
And the answer to that is no. We're not limited to the charge capacity by decreasing the size of the Orbitrap Elite.
Okay. And we actually just have time for one more question, and it is ETD performance could be lowered due to tighter folding, CC?
Yeah, that's a good point. I neglected to talk about that, but yeah, in this case, the HCD data was probably better than the ETD data because disulfides are known to have high electron capture affinity. So some proportion of the electrons that are being transferred go into breaking disulfides and not breaking backbone. So that did decrease the efficiency of that reaction a little bit relative to HCD. In general, when there isn't a disulfide, there isn't something that is kind of an electron sink, ETD should be producing, in general, more sequence coverage than the collisional activation techniques.
All right. Thank you, Dr. Horn. Our time is up. Thanks for listening in, and thanks for the great questions. This webinar will be archived for 6 months on our website, www.genengnews.com. If you missed parts of it, you can watch it again or you can recommend it to friends and colleagues. Once again, I want to thank Dr. Horn as well as our sponsor, Thermo Scientific. We'll be sending out a survey shortly and hope you'll take the time to respond. Your comments help us continue to provide topical and timely webinars. Thank you very much.